Alright, students, let's go ahead and look at section 8.4, and it's a pretty short section. We're going to look at one major concept we call Bayes' theorem, and this has a lot to do with probability trees and given probabilities. So let's take a look at this example, okay, on tuberculosis screening. Okay, so first of all, this says a new inexpensive skin test is devised for detecting tuberculosis. To evaluate the test before it is used, a medical researcher randomly selects 1,000 people using precise but more expensive methods. It's found that 8% of the 1,000 people tested have tuberculosis. Now, if you begin to look down at the tree diagram, I just want to pause there. This would be, T would be tuberculosis. T prime is they don't have tuberculosis. So 8% or 0.08. The rest would be 92%. So you don't have to be given that 92%. You figure that out. Okay, so that's what we have so far. 8% have tuberculosis, 92% do not. Now let's read on. Now each of the 1,000 subjects is given the new skin test, and the following results are recorded. The test indicates that 96% of those who have it and 2% of those who do not. Okay, so this is what it's saying is the skin test, 96% have the tuberculosis, meaning 4% do not. And this is based on the skin test. So that's how that goes. And then it says 2% of those who do not. So out of these who don't have tuberculosis, the skin test shows that 2% have that. Okay, so that's what that says. All right, so what we're going to do with this now says, based on these results, what is the probability of a randomly chosen person having tuberculosis given that the skin test indicates the disease? All right, so let's kind of take a look at what we have here again. So again, we had 8% have tuberculosis, 92% don't. And then based on the skin test, out of this group right here, 96% are shown to have tuberculosis based on the skin test, whereas the 4% are shown to not have it. You go down here with the group that does not have tuberculosis, 2% show that they do have tuberculosis based on the skin test. The remaining 98% show that they do not have tuberculosis. All right, so think about that and make sure that you understand where all those numbers are coming from. Now, the question is, this is the probability of having tuberculosis, which I'm going to write as T, given the bar, like we've learned, that the skin test indicates the disease. So in other words, we're looking for the probability of tuberculosis given that the skin test says you have the disease. Okay? All right, so when we put this together, we're going to use what we call Bayes' formula. So we're looking at the probability of T given S. What we do is we do the product of the branch probabilities leading to S through T. So what that's going to mean is you're going to end up at S going through T. So that's going to be the product of those two probabilities there. Okay, that's what that numerator is going to say then. Okay, then what you do is you look at the sum of all branches that go to S, that go to the skin test. So if you look at that, okay, the skin test would be, you would end up here or you would end up here. So you would go through this part, the 0.8, 0.96 again, and then you would go through this part, the 0.92 and the 0.02. And that's all the possible ways to get to S, okay? So the way you're kind of looking at this is you want to end up at S, and then you want to end up with S that way. Those are the two possibilities. That's the way that leads through T, or leads to S through T. All right, and that's what you do then is you work this out, and you can work this out on a calculator, and you would get 0.81, okay? So that would be the idea of what Bayes' formula is based on a probability tree. And just to show you the calculation, the numerator, you would go 0.08 times 0.96. Good idea when you're doing this on the calculator, just do the numerator and record it. So that would be 0.0768. And then the denominator, you just take that, same thing, 0.08 times 0.96, and then add to that the 0.92 times 0.02. Okay, and then we'll record that. And then just divide that out. Okay, so you could go 0.0768 divided by 0.0952, and then that'll give you the answer that's been rounded up. So that's roughly about 81%. All right, so what this is saying is the skin test is verifying it in 81% of the time. All right. Okay, so here's what Bayes' formula is saying. It's a little easier to demonstrate than it is to write in symbols, but what you're doing is these are mutually exclusive events represented by U in your sample space. So if you're looking at the probability of some specific event happening given E, then of course we've learned this formula. It's the intersection divided by the probability of getting to that event. And that's kind of what we did on this last problem. This was the probability of getting to S, and then this was the probability of going through T and S at the same time. So that's the intersection. This part right here is the probability of T intersect S, and then those two things added together gives you the probability of S, all right? So that's how this would work. The formula on this would be probability T intersect S all over the probability of S. Okay, that's what we really did on that. Okay, and what this is saying is this is just a sum of all of the branches leading to E. That's what that denominator is saying. Okay, all right, so let's go to the next page. Now what I'm going to do on the next page is just learn how to crunch out the probability trees. And this is probability tree. You're given individual pieces of information on this. Now, the first thing we're going to do is just, so you can follow along on, let's just label everything. So this A is 0.6, B is 0.4, C is 0.9, D is 0.1, E is 0.7, and F is 0.3. Okay, now what we're going to do on this problem is we're going to find the probability of X given A using Bayes' formula. So what we really do on this is we do the probability of the intersection of those two events divided by the probability of A happening. Okay, so first of all, you would just want to look at this. What this means is you want to end up at A going through X. So I'm going to write this as the probability of making it to A going through X, and then the denominator is just going to be the sum of the probabilities of getting to A. Okay, so sometimes it's kind of good to understand how this goes in words. That's what Bayes' formula is saying. Okay, so we want to make it to A through X. The way to make it to A through X is to go through those two probabilities. Okay, so that'll be the numerator, and we multiply those things out. So it's going to be 0.6 multiplied by 0.9. Okay, then we're going to look at the sum of getting to A. There's more than one way to get to A is what I should have said here. Okay, So if you're going to get to A, you got to go that way and you got to go that way. Those are the two ways to get there. So that would be same thing, 0.6, 0.9, and then plus the other branch would be 0.4 times 0.7. So that's the setup of that problem. Then you can take your calculator. So you can do this in your head. 9 times 6 is 54. You have two decimals, so that's 0.54. Denominator, this part right here is 0.54. You can do this in your head. 4 times 7 is 28. So that's plus 0.28. So now we get 0.54 over, and then you can add these two things together. When you add decimals without a calculator, you line up the decimals. So that would give 0.82. Now I want to show you kind of what you could do on your calculator. You can certainly do this. I want to show you how to get an exact answer though too, both with and without your calculator. So I go 0.54 divided by 0.82. Then we can round that, so that should give about 0.659. So that will be the approximate probability on that. That gives that answer there. Okay. Wanted to show you another thing you can do, which I think you want to know how to do, is in this case, if you have 0.54 over 0.82, you can get rid of the decimals. Both of the decimals need to be moved over 2. The way that you actually are doing that technically is you're multiplying the numerator and the denominator by 100. If you wanted to get rid of 3 decimals, then you would multiply by 1,000, for example. So if you do this, this would just give this. This would give 54 over 82. Then you could reduce that fraction. Okay, I think, well, I both divide by 2, I know that. So if I did that, that would be 27 over 41. Okay, so if you wanted a fractional probability, that's how you could do that. And you could also do this. Once you get this computed on your calculator, I've shown you this before lots of times, you can go math, fraction, just press enter, and that gives you 27 over 41. Okay, so that's how that works out then. Okay, so let's see. I think what I'm going to have you do now is go ahead and pause the video if you need to get this done. I'm going to go ahead and move down and let you work out the next problem. Okay, so I'm going to have you try this and see if you do this correctly. Now notice on this we're looking for exact fraction answers. Okay, so that's the reason I wanted to show that to you. Okay, so go ahead and let's start working on that. Pause the video, come back when you're ready to check and see if you got the answer. You should get 1/3. So just, if you get that, then you're in good shape. Okay, moment of truth. Let's see if we did what you were supposed to do here. So first of all, I just labeled these things and did the labeling here. I want to point out a couple of things. Notice that when you branch out in 2 directions, these should always add up to 1. So 0.8 and 0.2 adds up to 1. You branch here 3 directions. Notice that 0.6, 0.2, and 0.2 also add up to 1. And same thing here, 0.5, 0.4, what adds up to 1? So that's the way your probability tree should work. Okay, so what we do is we're doing the probability of M given Q. And by definition, that's the probability of the intersection of M and Q divided by the probability of Q. That second thing always goes there. Okay, well, the intersection, this just means you're going to make it to Q going through M. So that's that branch that I have highlighted in yellow. So that's 0.2 times 0.4. Then the probability of Q, see there's 2 ways to get to Q. You can go 0.8, 0.2, 0.2, 0.4. Okay, so that's what I highlighted in blue. That's the calculation. Numerator is 0.08. Denominator is 0.16 plus 0.08. So you get 0.08 over 0.24. If you went to your calculator and did this, what you're going to do is just get a bunch of repeating 3's, which is what 1/3 is. So I multiplied by 100, changed it to 8 over 24, reduced the fraction. Okay, so you want to know how to do that okay. So hopefully we did okay. If you did that okay, then you understand the tree diagram, the given probability and Bayes' theorem and how it works. Okay? All right. So hopefully everybody's getting that okay. Okay, moving on to the next example. We're going to kind of talk through this example of Bayes' theorem. So ultimately what you'll be doing a lot of times is taking a scenario, putting together your probability tree, and then using Bayes' formula to interpret the problem. So let's read this one kind of carefully and see what this says. Okay, this company produces 1,000 refrigerators a week at 3 plants. Plant A produces 350 refrigerators a week. I'm going to kind of work this out as we go. Plant B produces 250, and Plant C produces 400. Now right there, that's going to give you probabilities. See, there's 1,000 refrigerators. So Plant A, you're going to have 350 over 1,000. Plant B, you're going to have 250 over 1,000. And then Plant C, you're going to have 400 out of 1,000. Now you can change those on your calculator if you want to. A little trick on this, if your numerator and denominator end in zeros, you can cross that out. So that's 35 out of 100. So see, that's going to be 0.35. This is going to be 0.25. And that's going to be 0.40. Now let me ask you a question. This is real important when you do this. What does these probabilities add up to? Yeah, they add up to 100%, so those add up to 1. Okay, so we have that. And then the next thing it says is production records indicate that 5% of the refrigerators at Plant A are defective. Okay, so that will mean that 95% are okay. All right. And then it says, so we got that 5% are defective, and then 3% at Plant B. So Plant B, you got 3% are defective. How many percent are okay then? Right, 97% are okay. And then C, it says 7%. So at Plant C, 7% are defective, therefore how many are okay? Right, 93%. Okay? So we got everything there. So now when we begin to build the tree diagram, what we have is Plant A, B, C. Notice that we have a 35% chance of, out of those 1,000 refrigerators, that one being produced in Factory A. And 25% from B and 40% from C. So that whole branch adds up to 1. Then we start branching out from here. So this would be 0.05 and 0.95. So 5% are defective, 0.95 are okay. That's the D and the D prime. D is defective, D prime is not defective. Then you have 3% 97, 7% 93. So you want to look at this information and understand how that's been put into that tree diagram. So the question now is, if a refrigerator at the warehouse is found to be defective, what is the probability that it was made at Plant A? So what that means is we're going to find the probability that it's produced at Plant A given that it's defective. Okay, so that's what that problem is saying. We found it to be defective. We ended up at the defective branch, but we went through Plant A. Okay? All right. So we're going to do that. So again, what we do on this then is, again, just like we did before, this is really the probability of A intersect D. And that would just mean that you end up at D going through A. So that would be that probability right there. And then it would be over the probability of hitting D. Well, there's several ways. There's 3 different ways you can get to defective. So that branch would go there, there, and there. So you have the 0.35, 0.05, 0.25, 0.03, 0.40, 0.07 like that. All right. So then this is just a matter of doing this on your calculator. I'm not going to go through the details of doing this on the calculator. So that's about a 33% chance that if you were kind of randomly given a refrigerator that was defective, there's about a 33% chance that it came through Factory A. So that's the idea. Okay? All right, so let's go to the next page. Now, what I'm going to try to have you all do is see if you can put this whole thing together yourself. So what you're going to do is the first part on this, you're going to find, construct the probability tree and then see if you can answer the question about that. So go ahead and pause the video and see what you come up with. Just use your calculator to get a decimal solution. Okay, so let's take a look at your calculation, see if you got this put together. When I was reading the problem, I kind of just jotted down the ideas. So you're looking at, it says 75% of the employees are satisfactory and 25% are unsatisfactory. So again, that means that that adds up to 100%. Then it said 80% of the satisfactory had previous work experience. So that means 80% have it, 20% do not. You have to figure that out, of course. And then it says out of the 40% had previous work experience out of this group. So that'd be 40% and 60% do not have work experience. So what I did is I just let S be the satisfactory workers, S prime is unsatisfactory, W is work experience, W prime is no work experience. You can use whatever variables you want. So on the tree it goes like this: 75% are satisfactory, 25% are not satisfactory. Out of the satisfactory group, 80% have work experience. The remaining 20% do not have work experience. Out of the 25% who are unsatisfactory employees, 40% have work experience, 60% do not. So that makes some degree of sense, I think. That's pretty logical. So now the first part says if a person with previous work experience is hired, that's the given part. That's what we're given, is that they have work experience. Then what's the probability they're going to be a good, satisfactory employee? So we're doing probability of S given W. So if you look at the tree diagram, we're going to W through S. So that's that branch there. That would be 0.75 times 0.80. Then you do the probability of getting to W. There's two ways to get to W, this way and this way. So 0.75 times 0.80. The other way is 0.25 times 0.40. So when I work this out, I got 0.6 in the numerator, 0.7 in the denominator. And when you have that, if you multiply top and bottom by 10 to get rid of one decimal, you just get 6/7. And 6/7, I think on the calculator, when I did that, I got 80.857, which I just rounded off then. Okay? So you can check your calculations when you do that. Again, I just kind of do things, the numerator and denominator separately. So the numerator, 0.75 times 0.80 gives you the 0.6. And then if you take the 0.75, which we've already done, times 0.80, okay, and then add to that the, what was it, the 0.25 times 0.40. Sorry, it takes me a while to get all this stuff put in here. So we get the 6/7. And again, you could just go 0.6 divided by 0.7. That gives you that approximation. So about 85%, 86% of your employees with work experience are going to end up being satisfactory. Okay? So that's how that goes. The second problem says if a person with no work experience is hired, so that's the given part. We're given that they have no work experience. What's the probability they'll be satisfactory? And I think a lot of people would think, well, it would just be the rest of the 85%, so it would be like around 14% or something like that. It's not necessarily the case. You follow Bayes' formula, this would be the probability of making it to W prime through S. So that branch is 0.75 times 0.20. They are, you make it to W prime, they're unsatisfactory through the branch S like that. That's what that means. And then there's two ways to get to W prime, so you're going to notice that's exactly the same. To get to W prime, you got 0.75 times 0.20, and then 0.25 times 0.60. So that's the calculation you get on this. So you ended up, I think, with this one, you should have got 0.15 over 0.30. That's just 15 out of 30, so that's a 50-50 chance, or 1/2 probability. So that means out of the employees that you hired that don't have job experience, about 50% of them are going to turn out okay. The other 50% you're going to drive you crazy, and maybe you're going to get fired or something. I don't know. So that's the idea. All right, so hopefully you did that okay with Bayes' formula. That's really the only concept in here. You're going to work a lot with probability trees and make sure that you can do the given probability based on the probability tree. So good luck in working out these problems. Have fun, as usual.